Okay. Okay, let me read out. At any temperature above 0 Kelvin, all particles have kinetic energy, and particles of solids have vibratory kinetic energy. That is to say, the ions of an ionic solid vibrate with a frequency that is same throughout that solid. And we call that as the natural frequency of the solid. Okay? And let me say omega be the natural frequency of that particular solid. I don't know whether you understood anything or not. Okay, but this is something which you have already learned in your thermodynamics in your intermediate and even in your lower classes also. Okay, you might not have concentrated, but let me give you a simple review of it. What's temperature? Will somebody answer? What is temperature? Yeah,
The amount of hotness or coolness in a given place.
it's not amount, it is a measure of hotness or coldness of the body, right?
Okay.
It's a
Yes,
measure,
sir.
right? Okay, good. What is hotness? Yeah, I mean, we use the word hot, right?
Heat present in a
Amma?
substance.
Quality,
Heat present in a
quality of being.
No, it's not the quality of something. Okay, somebody else is answering something. Yeah.
the amount of heat present in a substance.
Oh, good. Very good. Okay. Yeah, you made it very simple. Okay, very good. What do you mean by heat?
It's a feeling. It's a feeling, and we name it as heat.
దేవుడా
Energy, sir. Energy
ఫిజిక్స్
release.
కొడతారు ఫిజిక్స్ వాళ్ళు కొడతారు ఓకే
In the form of energy, sir.
గుడ్ ఇట్స్ అ ఫార్మ్ ఆఫ్ ఎనర్జీ వాట్ ఎనర్జీ
Heated.
very good okay excellent okay I mean I appreciate this kind of answers I appreciate this kind of answers okay so when do you say that the
At
energy is in the form of heat yeah
the
Sir, when there is
smallest particle.
difference in temperature, sir, from one body to
temperature
another.
is a measure of heat okay hotness right temperature is a measure of hotness what is
Smallest
hot
particles,
Amma?
highest speed.
Good,
Quantum
good. Very
particle.
good. Very
Energy
good. Very good.
transfer, sir.
యాక్చువల్గా మీరు ఎందుకు అంత కష్టపడుతున్నారో నాకు అర్థమవుతుంది నా క్వశ్చన్ అక్కడ ఆన్సర్ నేను రాశాను కదా అక్కడ నేను ఇందాక చదివిందే నా ఆన్సర్ యూ పీపుల్ ఆర్ ఓకే సో డమ్ నేను ఆన్సర్ రాసి ఆన్సర్ చదివి మళ్ళీ క్వశ్చన్ అడిగితే ఎక్కడో ఆలోచిస్తారు యూ గాట్ 5 seconds టు ఓకే ఆన్సర్ మీ 5 4 3 2 1 వాట్స్ ఇట్
They have vibratory kinetic energy.
Right. Okay. Whenever you say that the body is hot, that implies its kinetic energy is very high. When you say the body is cool, that implies kinetic energy is less.
Yes.
Okay. Now this kinetic energy may be a translatory kinetic energy, vibratory kinetic energy, or rotatory kinetic energy. Okay. There
Stated.
are so many ways. Okay. But right now I'm not talking about all of the things. I'm talking about a solid. Okay. In that solid, okay, we'll consider that it has got vibratory kinetic energy. Okay, so temperature is a measure of the vibratory kinetic energy of, it's not just vibratory, okay, all the possible okay kinetic energies that are possible okay available inside the material, that's what is your temperature measuring or temperature trying to tell you. Okay, so what do we have is whenever the temperature of a body is above 0 degrees Kelvin, it will have vibratory energy. And if the temperature of the body is same throughout, it will have a natural frequency. It will have a natural frequency. It will be vibrating with a natural frequency that you call it as omega. Okay. So already you have learnt in your intermediate and so that every existential object will have a natural frequency. That means everything which is made up of a similar kind of structural arrangement will have a natural frequency. Okay. Let me suppose I am taking an ionic solid, and that ionic solid has a natural frequency omega. That is what is my first paragraph meaning. Okay, let me consider that I am taking a solid, ionic solid, with the natural frequency omega. Okay, now in the left hand side we have a cation and an anion, a cation and an anion. Okay, now in the zero field, these are in these positions. I'll apply some electric field. When I apply some electric field, this cation got displaced by x1 distance and anion got displaced by x2 distance, because of which there will be a net dipole moment produced. Sir, okay, here you have your cation and here you have a anion. So anion and cation are separated by some distance. Then okay, don't we have dipole moment here? No. Sir, why can't we have? Please, okay, remember, okay, this figure that I just explained. Okay, please remember the figure that I just explained here. Okay, please remember the figure that I have explained here. Okay, one second, Amma. Give me a minute. Okay, so please remember, okay, if you're talking about a cation and anion inside the crystal lattice, okay, without the field, they will be at the same point. They will be at the same point. After applying the field only, they get separated. Okay, so after applying the field, the cation got displaced in one direction and anion got displaced in another direction. That is what is shown here. Okay, please remember that part. Okay, whatever okay explanation I gave over there in the previous two slides. Okay, that is what is to be applied. So cation got displaced by x1 distance and anion got displaced by x2 distance. Sir, why should the distances displaced should be different? x1 and x2 enduku xx enduku teeskoru? Simple. Cation mass is different and anion mass is different. Okay, so I have considered a cation of mass m1 and an anion of mass m2 because their masses are different, though their force is same. Why is the force same, sir? Both of them have got charge q and both of them are in the electric field E. So the force experienced by both of them is q into E, though they will be in opposite direction. Though they will be in opposite direction, the force is same. Because they are experiencing same force and having same different masses, the displacement they get, the displacement they get will be different. Okay, so let me say x1 is the displacement of cation and x2 is the displacement of anion, because of which net dipole moment gets generated. Why? This is x1 plus x2 anamata. Okay, whatever you see in this figure here, whatever you see over here, okay, the distance between those two, okay, negative charge center and the positive charge center will be x1 plus x2. Okay, and the charges is q. Okay, and the charges of these two things is q. So the dipole moment produced because of the applied electric field is Ze, that is the charge of the atom or whatever. Sorry, it is not Ze. Okay, it should be okay E, or let me put as okay E. So why, sir? If it is okay sodium chloride, you'll have one unit resultant charge. If it is okay, let me say sodium magnesium chloride, okay, then this will be okay 2 units. This will be okay, charge will be 2 units. Okay, what will I do? I'll write it as okay small q. Okay, q. Okay, small q is the charge. Okay, so when small q is the net charge of the ion, net charge of the ion, and the separation between the two charge centers is x1 plus x2, then the dipole moment is nothing but okay q into x1 plus x2. Okay, why did I change from capital to small? Because all these here are capital, so I'm using a capital here. Okay, so the net dipole moment produced is mu, which is equal to q x1 plus x2. Okay, good. After producing the dipole moment, okay, will they stop? Yes, they stop. Why do they stop? Because there will be a Coulombic force or restoring force. There will be a restoring force. Okay, I told you that they will be oscillating with the frequency omega. And again, from okay, restoring force is proportional to x or minus x, or restoring force is equal to k into x, where k is the restoring force constant, or you sometimes call it as spring constant. Okay, so F is equal to minus kx, or acceleration is equal to minus k by m into x. Okay, acceleration is force is mass into acceleration, so acceleration is equal to force by mass. So it is nothing but minus k by m into x will be the acceleration. Okay, acceleration is d square x by dt square. So this is a differential equation. So the differential equation of the, okay, when you solve the differential equation, you get the solution as a, okay, x is equal to a sine omega t plus theta, something like that. Okay, now what is omega? Omega is nothing but under root k by m. Omega is nothing but under root k by m. Okay, that implies omega square is equal to k by m, or k is equal to omega square m. K is equal to omega square m. Okay, now, okay, after this explanation of your intermediate part, let me come back here. So the dipole moment produces, okay, Q. Let us keep it aside. If M1, M2 are the masses of the ions, the force experienced by these two masses will be ZE into E. Okay, or okay, say Q into E. Okay, let me not say there's ZE. Let me say E into E or Q into E. Okay. Due to this displacement of ions, there will be a net restoring force, that is Kx. Okay, which is equal to the deforming force QE. At equilibrium, in equilibrium again, okay, this restoring force will be equivalent to the deforming force. Deforming force is the Lorentz force and restoring force is, yeah, okay, Kx force. Okay, so K1 x1 is the force experienced by mass m1 and K2 x2 is the force experienced by mass m2. Okay, both of them are equal to the Lorentz force, that is Q into E. Both of them are equal to the Lorentz force Q into E. So K1 is equal to omega square m1 and K2 is equal to omega square m2. Very good. But we know that x1 is equal to QE by K1, QE by K1, and x2 is equal to QE by K2. So K1 is equal to omega square m1, and here we have x1 is equal to QE by omega square m1 and x2 is equal to QE by omega square m2. Aim special ga cheppindi ledu. I did not say anything special. I just substituted these two aspects in over here. Okay, what is this K? Okay, Kx is a restoring force on mass m1. K2 x2 sir, restoring force on mass m2. That's it. Okay. What is K? Okay, you know that we have defined omega square is equal to K by m, or we have already known. Okay, we already know that omega square is equal to K by m. So K is equal to omega square m. So here m is m1 and m is, okay, m in the, for the second mass is m2. So that's what I did. After doing that, I tried to calculate the ionic polarisability. Okay, sorry. This is ionic dipole moment. Ionic dipole moment is charge into the separation between the charges. So that is Q into x1 plus x2. That's what I gave. And polarizability is again the amount of dipole moment produced. That's what is this expression divided by applied electric field, and this is your ionic polarizability expression. This is the ionic polarizability expression. Okay, right. Now with this, I stop my class today.